So now let's talk about work. So this is going to be split into two parts, work done by a constant force and work done by a variable force. So let's start talking about work done by a constant force. Work is basically energy transfer by the application of force. For work to be done, there must be a non-zero displacement. What does that mean? It means if displacement is equals to zero, that means no work has been done. So for example, let's take a very simple example. You get up from your bed in the morning and you do come to campus, you do all this work, you go to work, you eat, you do all of this stuff. And at night, you come back and you lie down on your bed again. Physics says you have done absolutely no work. And the reason is because your displacement from the starting point is equals to zero. So be very careful when defining your time intervals in which you are talking about your work done. The unit of work is, and hence also for energy, is the joule. Joule is defined as Newton meters. That means if 1 Newton of force moves an object 1 meter away, then 1 joule of energy or 1 joule of work is done. In SI system, 1 joule is represented as kilograms meter squared per second squared. Mathematically, the work done by a force is defined as F dot dr, where dr is the vector dot product, which by definition is going to be given by F delta r cosine of theta, where F is the magnitude of the force, delta r is the magnitude of the object's displacement, and theta is the angle between F and r. So now let's look at an example. A constant force applied to a box. Let's suppose you have a box and it's resting on top of the floor and you would like to move this box at some distance delta r. So you apply a force at an angle theta to this box. Now let's talk about how many forces are actually acting on this box right now. We know that there is a normal force that acts on it that's upwards because of the surface in contact. We also know that force of gravity always acts on it, which is downwards. Now, what is the work done by the normal force? The work done by the normal force is equals to 0. And the reason is because n is perpendicular to the displacement. So therefore, the work done will be 0. The work done by gravity is also 0. F is perpendicular to the displacement. However, the work done by the force is now going to have two components, one along the x-axis and one along the y-axis, as shown here. So only the component that is along the x-axis is the one that we are concerned about. So if I was to draw vectors head to tail from here to here, they would be drawn as one pointing downwards, which gives me Fy, and then one pointing this way, which gives me Fx. So the work done by the force F is actually equals to F dot dr, F cosine of theta delta x. So in most situations, we will also talk about the total work that is being done on this object. So the total work or the net force done on this object is a sum of the force applied plus the normal force plus the gravitational force. As we saw in the last slide, normal force goes to 0, force due to gravity goes to 0, and we are only left with the applied force. So the net work that's done on this object is a direct relationship between the force applied and the distance that that object moves. So we can sum this up and say the only force that gets utilized is the force that's applied in the direction of motion. And that is the only force that is responsible for doing the work. So let's look at an example. A ball is tossed straight up into the air. What is the work done by the force of gravity on the ball as it rises? So as we always do this, we will first consider a ball, and it is rising up into the air, right? And it is tossed straight up. What is the work done by the force of gravity? We know that the work done is going to be equal to the force that is going to be applied dot the distance that that object moves. So not knowing what the exact distance is, let's suppose that that distance that it travels is delta y. Okay? So now the relationship between delta y and F, what is the force that's being applied? The only force that's being applied on it is its weight acting downwards, right? So I can place that into here, mg, and I can place the distance that it travels here, like this. So the work done on this object is mg delta y. Okay? Very carefully note what this also is. This also is the equation for potential energy of the system. And we will talk about that when the next lecture comes. So now let's do another example. A box of mass m is towed up a distance delta x on a frictionless incline at constant speed. The applied force F is parallel to the incline. What is the work done on the box by the applied force? So as always, we will start by drawing a diagram and all the information that the question gives us. So let's first start with drawing our picture. Here's my box moving up, right? And this is the direction of our applied force. My angle here is theta, and the weight acts downwards, always. Now, the question is, what are we supposed to do now? The first problem to solve here is going to be, what are going to be my coordinate system, my chosen coordinate systems in which I'm going to base off this whole question with. I think I'm going to use these as my coordinate systems. Okay, x and y. Because this is probably the easiest way we could do this. So now let's resolve everything that we have in terms of the chosen components. So this is mg. This means this angle is going to be theta. This is going to be mg cosine theta. And this is going to be mg sine theta, right? And what are we required to do? We are required to find what is the work done on the box by the applied force. So my question is, work done will be equals to F dot delta x, right? So I need to find a relationship between F, which is the applied force, and the distance delta x that it moves. Okay? So in order to do that, I need to go back to what I already know, Newton's laws, right? So what are Newton's laws? Sigma fx and sigma fy. Sigma fx is going to be all the components that are along the x-axis, okay? Which are going to be my mg sine theta and my force. So I have an f, which is positive because of my chosen x, and I have a minus mg sine theta, which is because this points that way, head to tail rule. And fy is going to be, I have a normal. I totally forgot about that. So a normal that's directed upwards minus mg cosine theta. Now it says that it is a constant speed. So constant speed means that this goes to 0 and this goes to 0, right? What am I left with? So my equation 1 reduces down to F equals mg sine theta, and my equation 2 reduces down to n equals mg sine theta. Okay? This means that my work done here is mg sine theta. If I can plug that back into here, that's the solution to my problem. This is going to be equals to mg sine theta times delta x, and we're done. Okay, so the work done by the applied force is mg sine theta delta x. Now, in part B of this example, it says, what if the work done is not by a constant speed? What if the force actually increases the speed? That means we now have an acceleration introduced into our system. So literally the questions will remain exactly the same. So my work done will be the same. So for part B, my work done is still F dot delta x. However, my acceleration is there, so that means delta fx cannot be equals to 0 anymore. So for part B, instead of 0, I will have ma here, which is only along the x direction. Because of my chosen direction, it's going to go upwards, right? So my net F in this case, sigma F, will remain. The applied forces don't change. They will still be mg sine of theta. However, this is now going to become ma equals F minus mg sine theta. This means F now becomes ma plus mg sine theta. Oops, I ran out of room. Which will equals to F. So I can plug this value of F into here, and I will get ma plus mg sine theta delta x as my answer. So in two different scenarios, I will get slightly different work done. 1 and 2. So the moral of the story is Newton's laws and your force equations are really important. If you can write the force equations, you can do these problems easily.